I factor out the common terms. I've got a relationship between the net torque that I applied and the angular acceleration I get out of the object. So I have my rotational inertia, my first rotational inertia formula. For this particular system, this mass distribution, and axis of rotation, the rotational inertia formula is I equals mr squared. So with that, we can certainly, with our first formula, we can make sure that it does obey all three of our conceptual checkpoints. So first of all, according to this formula, if the point mass is larger, then the rotational inertia will be larger. That we just look at the formula. In fact, we can see they're linearly proportional. So if you double the mass, you'll double the rotational inertia. So that's checkpoint number one. Conceptual checkpoint number one is met. We said that more mass should mean more rotational inertia. Something's more stubborn to rotational motion as well. Let's check the other ones. According to this formula, R, if R is increased, we make the radius of the circle bigger. The rotational inertia should again be bigger. This is a square proportionality, which means that if you double R, the rotational inertia will be 4 times as large. So over here, we're distributing the mass further from the pivot, right? If we make this circle larger, the mass is further out from the pivot. So this is factor number 2. So we see conceptual checkpoint number 2 is manifested in this formula as well. In fact, that term also manifests the final one, because if you look at this system, it's just a point mass. So the center of mass of this system is here. So if you make the radius of your circle larger, you're also taking the center of mass further away from the pivot. So this final factor, factor number 3, is also there. In fact, if you wanted to make the rotate this object through the center of mass, what would you have to have R be? What would you have to do to put the center of mass at the pivot? 0. So if you had R equals 0, you get rotational inertia 0. Now that's a bit weird. You can't, that's pretty minimum. Can't have any less stubbornness to rotation than nothing. But it's also a bit of a pathological case, because of course, once you put a point mass at the center of the circle, there's nothing to a point mass. It has no spatial extent, so there's no resistance to rotation because there's nothing to rotate. That's of course not true for objects like this, where you have a barbell, right? Even if you put one mass at the pivot, the other one can't be. So in general, for bigger objects, even if you put the axis of rotation at the center of mass, there's still going to be some mass that's away from it. So the rotational inertia will be minimum compared to any others, but it won't be 0. So that's a little bit of a pathological case here. So that's certainly minimum, but it's a little bit pathological because there's nothing left to rotate in this case. It's a point particle. There's no extended shape to it. So if we have more extended objects, expect the rotational inertia through the center of mass to be minimum compared to other axes, but not 0. You can't put all the mass usually at the pivot if it has a bunch of mass in different places. So this is our first rotational inertia formula. It's for what you might think is an incredibly simplistic system. It's enough, I guess I should mention, we can get the units of rotational inertia. It's going to be kilogram times meter squared. There's nothing huge to be read into the units except for the fact that both they have ingredients in both mass and physical dimension, which is of course factors 2 and 3. But what do we do for other objects? Obviously, not every object we're going to be working with is going to be a single point mass rotating around some pivot on some massless rod. But every other object can be made out of this system, because a single point mass, any single object can be made out of a whole bunch of these. So let me talk about that. So this is the basis upon which we build all of our other rotational inertia values. So we split this off into two possibilities. We have either discrete collections of this or continuous collections of this. So for discrete collections, we just use it a bunch of times. You guys know the summation symbol? Okay. So I'll give you an example. When I mean discrete, I mean you can say there are 2 or 3 or 5 point particles. So something like this. Let's say you rotate it like this. You take each point mass, M1, M2, M3, M4, and you measure how far is each point mass from the axis of rotation. So this would be R1, R2, etc. And then just add up the total. Make sure that you always add. Rotational inertia is always positive. It's a measure of stubbornness. You can't have negative rotational inertia any more than you can have negative mass. It makes no sense. Every mass that you add to the system is going to add resistance to rotational change, right? Okay. So I have you do, I think, a barbell on the homework. And a barbell obviously has 2 point masses. It has 2 point masses and a massless rod connecting them. And I have you try out different axes of rotation through it, which will change the R1 and R2 values, but of course the masses are what they are. Now, that's the easy one, but you could also take some bizarrely shaped object, rotate that, and use the same idea. You can take the object and just pick and say it's made out of a bunch of point masses. Maybe you'd need a million or a billion of them in order to accurately represent that object, right? So think of it like pixels on a computer screen forming any image, right? So you could take this mass, M1, figure out how far it is from the pivot, and then do that a million more times, and then you could form that object, right? So there's a whole mathematics that's designed to do this. Take things, chop them up into very small pieces, and then very carefully figure out all of their contributions and integrate them into a whole. The process is called integration. It's what you learn in calculus. We are not going to do that because this is not a calculus-based physics class. So what we do is we just go to a table and read off the results of someone doing the calculus for us. So we get a table. You will find it on the second page of your formula sheet, which you probably have, as of yet, had no need for. Now you will. Okay? You just go and you grab the rotational inertia of the object that is appropriate to what you are doing. And you have to match it up. It has to be the right mass distribution, and correct axis of rotation. And there are pictures worth 1,000 words, so there's a little pictures there. Remember, it's really important that you pick the right shape. You can't just condense it into a simpler shape. You have to pick the right shape, because mass distribution is really important, okay? So you have to pick the right shape. So let me give you an idea of certain things you'll find there. For example, one of the ones that you'll find there is a solid disk, like so, with a total mass m and an outer radius r. So it'll draw you the shape. It also has to show you the axis of rotation because that is important as well. And it will tell you that the rotational inertia of this particular mass distribution and axis of rotation is 1/2 mr squared. It will also, here's another one you'll find there, a thin ring. So this is a thin ring of mass m, outer radius r. So I guess I should label these. This is the solid disk. And this is the thin ring. So all the masses are in a single location on the outer radius. The axis of rotation, that is the center of mass, that is shown, I believe. You might say, how are you going to spin it like that if there's nothing to attach it there? You might have to put on some very low mass, massless spokes. Okay, so like a bicycle wheel. Okay, bicycle wheel, basically all the mass is on the edge. The formula sheet will tell you that the rotational inertia for this is mr squared. The one thing I should point out is that if a dimension isn't mentioned, then its amount is not relevant. So for instance, this thickness is not mentioned, so that thickness can be anything. So this could be a disk, or if this got a little longer, you might call it a cylinder. And this dimension, if it's not doesn't matter, this could be as long as you want. So that could be a thin ring or a hollow cylinder. I don't know at what point it would be long enough for you to prefer one term over the other. Okay. So you don't have to know exactly where these two equations come from. It comes from the calculus. Why does this one have a half in front of it exactly instead of a third or a fourth? You don't need to know that. Just grab it off the table. But here's what I do expect you to be able to know is if all else is equal, they have the same mass and same radius, why is it that the thin ring has a larger value? Which factor, 1, 2, or 3, tells us that? Which conceptual factor? Number 2, the mass distribution. In the solid disk, the mass is distributed uniformly from the middle to the edge. Here it's all on the edge, right? So on average, the mass is further out. Factor number 2. The mass is distributed further out from the axis of rotation. So that's why we expect that the thin ring is going to have a greater value. So those are the kind of comparative things that I would expect you to want to be able to do. I don't expect you to know why this factor here is a half versus a third versus a fourth, but I want you to understand why it can't be like 7, okay? Because that would make it bigger. The rotational inertia of a thin ring is greater because the mass is on average further out from the pivot if they have equal masses. So it's a mass distribution thing. Let me give you some other examples of things you can find there. If you look on the equation sheet, if you have a bar of mass m and length L, and you rotate it like this in the middle, the rotational inertia is 1/12 ml squared. Not 1/2, make sure you copy that right in your notes, it's 1/12 ml squared. You don't have to know why it's 1/12. That comes from carefully summing this object up as a bunch of point masses. But if you look, you will also find that same exact bar of mass m, length L, rotated like this. And there, the formula sheet will tell you that the rotational inertia is only 1/3 ml squared. So while I don't expect you to know where those factors of 1/12 and 1/3 come from, I do expect you to realize why one of them has a larger rotational inertia than the other. Which factor tells us why this one is greater? 1, 2, or 3? Number 3, it's about axis of rotation. Because if you rotate this bar through the middle, and it's a uniform bar, its center of mass is going to be there. So that's the way to rotate that bar so that it gives you the least stubbornness to rotational change. Whereas if you rotate it around the edge, you're rotating it significantly away from its center of mass, and it is going to present more stubbornness to rotational change when it's rotated like that. Okay? And again, if a dimension isn't mentioned, it doesn't matter. So this can be anything. This could be a bar, or it could be like a panel. At some point, if it's thick enough in that dimension, you might call it a panel instead of a bar. So you can go to the table, and you can get your rotational inertia values for extended objects. Make sure it has the right mass distribution, and axis of rotation. If you don't find it there, you may be able to build it out of these things. Okay? So let's say someone gave you an object which was like a sphere stacked on top of a bar with like a point mass sticking out of the middle, okay? And you rotated it like this, you could construct that. You would add up the rotational inertia of a sphere through its center of mass, plus the rotational inertia of a bar. So this would be the sphere, plus the bar, and throw in a point mass while you're at it, okay? That's just mr squared. But when you start adding these rotational inertias, it's really important to wind up with the right shape, okay? You can't just condense these down into the center of mass, okay? And by the way, that would be hugely problematic over here, because of course, if you condense the ring and the disk into the center of mass, there'd be nothing left to rotate anyway, right? Those are rotated around the center of mass, and we need some mass that's not there to get a sense of stubbornness to rotational change. Okay? So that's basically what you do. That's your prescription for finding the rotational inertia. If you can count that it's a number of discrete point masses, just use the point mass formula a couple different times, however many point particles you have. If it's continuous, you immediately jump to the table. Don't try to condense it into a simpler mass distribution than it is, because mass distribution is important. And if you don't find your desired object on the table, you may be able to construct it out of things that are on the table. Okay? So that's a little bit about how to find rotational inertia. And at this point, let me give you an overview for homework number 9, and then we'll be all set. Here's your strategy. This right here is your strategy for rotational inertia. What do you do with that? Well, of course, it goes into here. So pick the appropriate rotational inertia. The rotational inertia is your link between how much torque you apply to something and how does it angularly accelerate. To get the net torque, of course, you add up all the individual torques. To calculate an individual torque, you have to use our RF sine theta. Remember that if there is actually no rotation, you can use any pivot you want and set up the torques that way. But if there is an actual rotation, then you have considerably less freedom. You have to use the actual pivot. Okay? So that's how you get from external influences into net torque. And then, of course, on this side, if you're lucky enough that if alpha is constant, you can use all your kinematics to relate it to how the thing will move. Okay? So you can relate that to omega initial, omega final, alpha t, delta theta, etc. And of course, one of the major applications that we had was your static equilibrium problems, where if alpha is 0, then you might use static equilibrium. Of course, that also requires that the net force is 0. So that's kind of like your master map for attacking homework number 9. Generally, the first half of the homework is going to be on static equilibrium. So you have those classic equations where you have net force is 0, net torque is 0. You find 2 equations to unknowns. And then on the back half of the homework, it starts to be that the torques don't all cancel. So you have some kind of net torque. That net torque is going to lead to angular acceleration. But you might need the rotational inertia of the objects to connect them. Okay? And I think there's one problem where you kind of have to think in left field. And hopefully by the time you get there, you're ready for it. And I should mention that this is really just the rotational version of what we did before. F net equals ma. So we learned how to do the net force addition. Of course, here, we allowed that there could be forces in 2 directions. So we generally split this up into x and y. And we had to balance we had to think forces in x and y directions. We luckily don't have to do that over here because there's only 2 possible directions for torque, counterclockwise or clockwise, but of course it is much more difficult to calculate a torque because it has other ingredients besides just the force. And then over here, if we were lucky enough that the acceleration was constant, which is not always the case, we can tie them into our kinematics. And if the acceleration isn't constant, well, there's one full coverage thing that will do it, whether the acceleration is constant or not. That's energy. Energy is your friend. Energy can do all sorts of crazy motions, whether the acceleration is constant or not. The one thing you give up, of course, is finding the time. Okay, so you can go ahead and mark in your notes. That's the end of homework 9 and exam 2 material. We'll start on post-exam 2 material, homework 10 on Thursday if we have class. Okay, that's it for today.